All right, if we remember a covalent bond was when two atoms are sharing electrons, and that bond is the force holding those two together. And those covalent bonds could be pure covalent bonds or polar covalent bonds. And so in a pure covalent bond, you have two elements with similar electronegativities, and they're each pulling those electrons equally. In a polar covalent bond, you have two atoms with differing electronegativities, and so the more electronegative an element is pulling the electrons closer to it. If we remember, electronegativity was a scale that electronegativity increases from this corner of the periodic table up into fluorine, which is the highest, which was set at 4. And you have to envision hydrogen is sitting over here above carbon. That's a pretty bad H, but that's where its electronegativity falls. It's 2.1 and carbon is 2.5. So what happens if we have, for example, a carbon atom and it's in a covalent bond with hydrogen, is that carbon is a little more electronegativity, so these electrons that they're sharing spend a little more time over near carbon than they do hydrogen. So you end up with one end of the molecule that has a slightly positive charge and one is slightly negative because the electrons are negative and they're spending more time over here and less time here. So we have a slightly positive end and negative end. And this is the dipole moment, and we would draw, that's a pretty bad arrow, but it's just an arrow with a positive end on one end. And this arrow can be, it's thought of as a vector where it has direction and magnitude. So it's pointing in the direction of the negative charge, and the length of the arrow is proportional to the disparity in electronegativity. And if we looked at something like boron and it was connected to fluorine in a covalent bond, then fluorine is much more electronegative than boron. And so we would have an arrow like this, but it would be bigger than that arrow because the relative difference in electronegativity, carbon is 2.5, hydrogen is 2.1, so there's not a big difference. But if we look at boron, it's 2, and fluorine is 4, so it's a much bigger difference in electronegativity. And this also gets incorporated once we start looking at molecules. When we did our VSEPR and looked at the shape of molecules, remember that carbon dioxide looks like this, right? And if we look at our electronegativities, carbon is 2.5 and oxygen is 3.5. So the electrons in these bonds are being pulled a little bit more towards oxygen than they are towards carbon. But when we draw our little arrows, and it's hard to tell from there, but they're equal in size because both of these oxygen are pulling with the same strength, and they're opposite in direction because this is a linear molecule, right? This is a type AB2 molecule where the electronic, or where it's electronic geometry is linear, and also the molecular shape. And so when you have two forces pulling in equal and opposite direction, they cancel each other out. So overall, this molecule does not have a polarity or a dipole moment. But if we look at something like our water molecule, right, where we have two hydrogen connect to an oxygen, hydrogen's electronegativity is 2.1, oxygen is 3.5. And when we did our VSEPR diagram, we found out that this molecular shape is bent. So these hydrogen are being pushed down because, remember, we have two pairs of non-bonding electrons up here, and that electrical area of high electrical density pushes down these electrons down here. All right, so each of these bonds would have a dipole like this, where the electrons are being pulled up towards that oxygen. And so when you have two forces coming together like this, the overall direction of that charge is straight up. And so this would be what we call a polar molecule, because you have one end that's slightly negative and one end that's slightly positive. So by looking at the Vesper process to figure out the shape of the molecule and looking at the individual bonds within the molecule, you should be able to predict if that molecule is polar or non-polar. And if you have symmetrical molecules, the dipoles tend to cancel each other out because they'll be of the same magnitude and they will be canceling each other out. But let's look at something like carbon tetrachloride. So what we'd end up here is this tetrahedral arrangement like this, and you can see that chlorine is more electronegative than carbon. So what you would have is a dipole in each of these directions. But since the molecule is symmetrical, they're going to cancel each other out, and overall we would not expect polarity. But if instead of CCl4 we had CH3Cl, right, then what we're going to end up with, we would draw our carbon, we could put our hydrogen down here, this hydrogen here, another hydrogen sticking out, and then we'll put our chlorine up here. All right, so in this case, carbon is more electronegative than hydrogen, so each one of these is kind of pushing up towards the center of this pyramid, but chlorine is more electronegative than carbon, and so once we're pushing up to the middle of this pyramid, we also have an arrow going up. So we would expect an overall charge on this molecule where this top part is a slightly more electronegative, or has slightly more of a negative charge, and then this bottom end has slightly more of a positive charge. So although they're both tetrahedral shapes, since this one is symmetrical and everyone's pulling away from the middle in equal and opposite directions, it's nonpolar. But in this case, everything is flowing up towards this top portion. So you have a slightly negative end and a slightly positive end, and you'd have a polar molecule.